Hello everyone, so welcome back. In the previous video we saw about the basic terms and definitions and the concepts involved in electrostatics. So now we need to dive further into the derivations and applications of what we learned. So in this video let's learn about electric flux. So electric flux is again a concept that needs to be introduced to proceed with the further derivations. So what is an electric flux? In the last video I have said that electric field lines represent how strong an electric field could be at a point. And now electric flux is a concept that we have introduced to define how strong an electric field is at a point. So I'll just write the definition of electric flux and then we'll see to understand how it works. So now we are learning about electric flux. And it's represented by the symbol phi. So electric flux is a quantity that represents the strength of the electric field at a point, at a surface. Okay, so this is the definition of electric flux, but now let's see how it is and what it's based upon. So you can note it down if you want. So let's consider a surface. For simplicity, we'll go with a plane. So you have a plane in free space. And we need to get electric field lines that are parallel to each other for study purposes. But if you place a small charge, what's going to happen is that charges emit electric field lines radially outward, that is in the form of circular paths. But this would not help us with our study. We need something that will produce parallel lines. So what we do is we take a charge that is really big compared to the surface, so that we can assume the electric field lines coming out of it are parallel. So let's consider a charge that's really big and it's not in the paper. So the electric field lines are going to be parallel. Now the electric flux linked with this paper, with this plane, is proportional to the area of this plane. And let's call that S, surface area. And it is also proportional to the electric field strength. So when you combine these proportionalities, the flux is proportional to ES, that is the product of the surface area and the electric field strength. So now let's try to make a quantitative representation out of this. I'm going to take a piece of paper and let's see how the orientation of paper is going to affect this flux. If I'm placing the paper perpendicular to the field lines, that is, the angle which the field lines makes with this paper, with this plane, is perpendicular, then how much of the electric field lines can this paper cover? So that is going to be from the lower end to the upper end. This is the total area which this paper, when oriented perpendicular to the field, can cover. But now what will happen if I tilt this paper a little bit? So I'm going to place this paper over here and I'm going to tilt it this way. Now it's no more perpendicular to the page. So when tilted, the lines are going to cover only a distance from here till here. You have seen that the area has significantly reduced. Now only this much of field lines can pass through the paper, whereas in the previous case a larger amount could pass. So there's one more quantity missing in the proportionality, and that is the angle the paper's vector makes with the electric field line. Now what do I mean by the paper's vector? So this is how it works. Any given surface will have a vector representing its direction. So that is always perpendicular to the surface. So if you have a plane like this, its area vector is perpendicular to the surface of itself. This is the area vector of this plane. And now if you have a plane that's tilted, that is in this way, the area vector is still going to be perpendicular to the plane, but now it's going to point this way. So these are the vectors which describe a plane. So let's try to bring this formula in terms of the angle this vector makes with the field of the plane. So you have the electric field lines and you have a plane. Okay, so now the area vector of this plane can be in both the directions. One either in this direction, perpendicular, or the other one in this direction. Both are being perpendicular. So let's consider any one. So let's consider this direction. So this is the area vector which the plane has with respect to the electric field lines. And this angle, theta, where theta is the angle between field line and area vector. The angle theta is the angle between the field line and the area vector. So it's directly proportional to the cos of this angle. So there's one more proportionality, that is cos of theta. So why cos of theta? So to get the maximum effect out of the present field lines, you need the field lines to be perpendicular to the plane. Because we have seen the previous demonstration, when electric field lines strike perpendicular, you can cover more area than when it is tilted at an angle. So we are trying to convert the lines which are already present in perpendicular direction. So when you resolve the components, which you have learnt in grade 11 about resolution of vectors, so we are going to resolve the vector into the perpendicular component and the horizontal component. So if this is the given vector, area vector, you are going to resolve it among the horizontal component, and the vertical component just vanishes away because of the presence of many similar components in opposite directions. So when you resolve this, you get cos theta. Magnitude of the area vector is always taken to be 1 because it's just a reference for the direction and it has no physical significance. So upon resolving this component, cos theta equals this vector which we require, quantity unknown, x by a. And you find a to become x to become a cos theta, and the value of a is just 1. So you get the cos theta component. So when you combine all the equations that we have done so far, we are finally going to get, we don't need a diagram anymore. We are going to get the flux is equal to E S cos theta. This is the formula for electric flux. So you can write this in another way, that is E dot S, where dot represents dot product, scalar product. E dot S is same as Es cos theta. So this is the equation for flux. Now based on this equation, you can find out at which point you are going to have the maximum value of flux, minimum value of flux, and intermediate. So let's just try the 3 different cases for understanding. So let me just write it over here. Flux is equal to Es cos theta. So let's take 3 cases. The first case, when the electric field lines are perpendicular to the field. The second case, when the electric field lines are parallel to the field. This is when the flux is going to be 0, because you can see that the angle of the area vector is actually just perpendicular. We have seen that. But the angle that this makes with the field lines is also 90 degree. And what is cos 90? Cos 90 is actually 0. So flux is 0 in this case. What about this case? In this case, the area vector perpendicular to the plane makes an angle of 0 degrees with the field lines. The field lines are in the same direction as that of the area vector. So here cos theta is going to be cos 0, which is 1. So flux here is going to be Es. This is the maximum value and this is the minimum value. And you can take any other intermediate case and substitute the value of theta to get an approximate value. So this is the last concept which is required to proceed to the derivations of this chapter. So you just need to remember that flux is equal to Es cos theta. So now we have seen on electric flux. So in the next video, we will go into the derivations, that is the derivation for electric field at a point due to an electric dipole, and then we have the Gauss law, and then we have the applications of Gauss law where we find the electric field due to a spherical shell and such similar objects. So this is it for this video. I'll see you in the next video and stay tuned.